Hello everyone, welcome to the first lecture of the week 7. In this lecture, we will explore Lagrange mean value theorem mathematically as well as with the problem. So, with some of the applications to solve those problems using the Lagrange mean value theorem, we will explore in this lectures, right? So, what will be the statement of the Lagrange mean value theorem? Lagrange mean value theorem, as it already contains a term mean, that means it is between some of the terms, right, some of the numbers. So, it says that f be a function that fulfills two hypotheses. F is continuous in a closed interval a b and f is a differentiable in an open interval a b, then the slope at some point c, where c lies between a and b, any point, interior point c, the slope at that point can be calculated using the value of the end point. So, how can you use that? The formula says that f dash of c is equal to fb minus fa divided by b minus a. That means if I knew the function is continuous and differentiable in an interval, then for any function, for any point c, the slope of that function at that point can be calculated using the ratio of the difference between functional value fb minus fa divided by b minus a. That will be a good approximate for the slope. It will be it is also in the term of Lagrange mean value theorem. The statement may be vary from author to author. The statement has the same meaning if I use theta from 0 to 1 and if I use that f dash of c in terms of theta itself, right. So, that's I have avoided here, but if the time permits or if we are interested to do this or if some problems came out to use the theta type of the Lagrange mean value theorem, then we will use that one as well, right. So, here Lagrange mean value theorem, only the statement says that if f is a real valued function from a closed interval a b and if it is a continuous in that closed interval as well as differentiable in an open interval a b, then the slope at any interior point can be calculated and that will be fb minus fa divided by b minus a, right. And it will be happen, that means the c must, at least one point c must be at that slope, right. So, that will be the conditions, right. There at least one point we have c in AB such that the slope is equal to the ratio of the functional value divided by argument values. How to prove this one? To prove this one, you have to construct a function first. So, imagine a function phi of x such that it is equal to f of x plus a into x, where x belongs to closed interval a b and a is any constant which is unknown constant which is to be determined such that phi a equal to phi b. So, we have a constant a such that phi of a is equal to phi of b, and we had already defined phi of x equal to fx plus a into x, right. So, that means a can be written as f of b minus f of a divided by b minus a, right, because you have already says that this is phi a phi b. So, phi of a is equal to what? Phi of a is equal to f of a plus of a into a, phi of b is equal to f of b plus of a into b. So, I mean subtract from this to this, you will get phi of b minus of phi of a is equal to f of b minus of f of a and plus a into b minus of a, right. And since a must be determined such that phi a is equal to phi b, so this is equal to be 0. Once it is 0, therefore a can be calculated as fb minus fa divided by b minus a. So that's why a is calculated as fb minus fa divided by b minus a. Now the function phi x being the sum of the two continuous function. See here, fx is a continuous function by the hypothesis, itself, and x is a continuous function, a is a constant function. So therefore, the sum of the two function, so phi x itself is going to be a continuous function. So it is going to be a continuous function itself, right? And derivable function. Similarly, it is a derivable function. Why? Because fx is differentiable function given in an open interval, a is a constant, x is a differentiable function in an open interval ab, and henceforth the sum of the two differentiable function makes the phi x as a differentiable function. So phi x is a continuous function as well as the derivable function, differentiable function. So phi x is continuous on a closed interval ab and differentiable in an open interval ab, and as well as we have chosen capital A in such a way that phi a is equal to phi b. So the third condition is also fulfilled here. Now, are you imagining about some other theorem which we had already listened, that there is a end points which are equal, that means it cuts on the horizontal line. So there must be some point lying between A and B such that the tangent line must be parallel to the horizontal line, or the slope at that point is going to be 0. So this is the three conditions which is going to be the Rawls theorem, isn't it? So we have a phi x, as a function which is continuous in a closed interval, is differentiable in an open interval, and the end points are equal. So this is the Rawls theorem. By the Rawls theorem, we knew that there must exist some point C in AB such that phi dash of C is equal to 0. So we are going to use that one, right? So C lying in an open interval such that phi dash of C is equal to 0. So that means phi dash of x is equal to f dash of x plus of a, and phi dash of c is equal to f dash of c plus of a, and this is going to be 0 by the condition of Rawls theorem. So this is 0 is equal to f dash of c plus a. So f dash of c is equal to minus a, and that will be f of b minus f of a divided by b minus a. As we had a here, right? So that means fb minus fa divided by b minus a. So we had calculated the slope at an interior point, and an interior point C of what? Of an open interval AB such that it is equal to FB minus FA divided by B minus A. That means it is equal to the ratio itself. The theorem simply states that between 2 points A and B of the graph of F, there exists at least one point where tangent line parallel to the chord AB. So what it says that if you have A here and the capital B here at the point A and B, right, then there must exist some point C which is parallel to this chord AB. So this is the chord AB, and the tangent line must be parallel to. So there must exist some point C here, right? So that is what geometrically we prove. Similarly, you can have A and B in these two, and here not only the single point, but there are two C1 and C2 exist between A and B such that their tangent line are parallel to the chord line AB, right? So that's what the Lagrange mean value theorem says. Lagrange mean value theorem also state that the C or here C are not unique, but you can have the several points between A and B such that the tangent line at that point is going to be parallel to the chord. That means the line making or connecting the FA and FB. A is what? A is nothing but it is FA, and B is what? B is FB. So connecting these 2 points, the tangent lines are parallel to that lines, right? That's what the geometrical meaning of the Lagrange mean value theorem says. Now let's have some examples and try to find out that those examples using the Lagrange mean value theorem, can we have some solutions? So first problem says that verify the function x square plus 2x minus 8 which satisfy the Lagrange mean value theorem in the interval minus 4 to 4, right? So how to verify that? And firstly, to verify that, you have to understand the Lagrange mean value theorem, the statement itself. The statement said the function must be continuous in a closed interval as well as it is differentiable in an open interval first. And then we will have the slope, a point C, where the tangent line at that point must be parallel to the chord joining the end points, right? That is our ideas. So firstly, let me give you one of the geometrical construction. So 4 and 4. So we must find out first f of minus 4 and f of 4, right? So what will be the value of f of minus 4? That is equal to 16 and minus of 2 into minus 4, and this is minus 8. So that will be 16 minus 8 minus 8, 16 minus 16 is equal to 0. What will be the f4? That is equal to 16 plus 2 into 4 minus 8. So that will be 16. So we have FA and FB. This is FA, this is f of B, right? 0 and 16, and that means the function is derivable. So we can find out f dash of x, f dash of x equal to 2x plus 2. That means this can be written as there is a some point f dash of c between the AB such that f of B minus f of A divided by B minus A. So this is equal to f of B. F of B is equal to 16 minus 0 divided by B. B equal to 4 minus of minus 4 is equal to 16 divided by 8 is equal to 2. So we are looking at a point between A and B, C, such that the slope at that point f dash of C becomes 2. That's what our idea is here, right? So that means we will find out this one. So f dash of x is given, f dash of x equal to 2x plus 2, and there this will give you f dash of c is equal to 2 into c plus 2, and that is given, that is equal to 2. So this means we have 2c plus 2, 2 to cancel out. So c is equal to, c is equal to what? C is equal to 0. So minus 4 and 4, 0 is the point where f dash of 0 is going to be 2, and that is true, right? Put x equal to 0 here, you will find out 2x plus 2 is equal to 0. So f dash of 0 here is going to be 0, right? So f dash of 0 is going to be 2 here, 0 plus 2 equal to 2, right? So that means we had verified the Lagrange mean value theorem in the interval minus 4 and 4 for a given function x square plus 2x minus 8. Similarly, that's the verification. Therefore, since c equal to 0 lies in the interval function minus 4 to 5, the Lagrange mean value theorem is validated. Example 2, verify mean value theorem for the function fx equal to x square minus 4x minus 3 in the interval a b, where a equal to 1 and 4. So, without looking any solutions, let me give you geometrical interpretations. So, here we have 1 and 4, 1 and 4. What we have to do, firstly look at the fx equal to x square minus 4x minus 3. We are looking for, this function is continuous in 1, 4. It is also a differentiable function in 1, 4. So, find out differentiability of this given function fx. So, this will be 2x minus 4, right. Now, I have to find out the end point values. So, I have to find out f1 is equal to 1 minus of 4 minus of 3 is equal to minus of 6, and f of 4 is equal to 16 minus of 4 cross 4 minus of 3 is equal to minus 3. So, we have 2 points here. So, as if I plot this one as a function, then we have what? f1 and f4. f1 is equal to minus 6. So, here we have minus 6. So, this is minus 6, and then we have f2 equal to this one. So, this point is minus 3. So, these 2 points are given, right. So, 1 and the minus 6 and the 4 and the minus 3 is given. We now find out some point C between 1 and 4 such that this will comes out to be, so let me give you f dash of C. So, assume there exists a point C belongs to where? 1 and 4, open interval 1 and 4, such that f dash of C is equal to f of b minus f of a divided by b minus a. So, let me calculate it. F dash of C is equal to FB, what will be the value of FB? FB is this one, right? This is FB, this is FA. So, FB equal to minus 3 minus FA equal to minus 6. So, this is minus 6 divided by 4 minus 1. So, this is equal to minus 3 plus 6 divided by 3. So, this will becomes out to be 3 by 3 is equal to 1. So, now I have a one point C lying between where? 1 and 4 such that its derivative or slope of at that point is slope of the curve of the function at that point is going to be 1. Now, I will find out that point C. So, to find out, look at f dash of x. So, what will be the f dash of x? So, f dash of C is equal to 2 into C minus 4, and this is given. This is how much? 1. So, 2C minus 4. So, this means 2C is equal to 1 plus 4 equal to 5. So, C equal to 5 by 2, that is equal to 2.5. So, and 2.5 lying between where? 1 to 4. Here f of 2.5 dash is equal to how much? This is 1. That is what we have find out. So, can be put here to find out it will be the same. So, f dash of 2.5, if I calculate directly, then 2 into 2.5 and minus 4 equal to 5 minus 4 is equal to 1. That means we have verified the mean value theorem, Lagrange mean value theorem for the given function fx equal to x square minus 4x minus 3 in the interval 1, 4. So, all these we have done this, right. So, C is nothing but C is equal to 2.5 or 5 by 2. Now, look at the third problem. Now, the function is given 2x square minus 4x plus 5, and you have to verify that it satisfies the Lagrange mean value theorem for the interval 2, 5. To verify the Lagrange mean value theorem, what we had? We have the two conditions. First Firstly, we have to check that fx is continuous, then fx is differentiable, and then find out the value of endpoints of the function, and then try to find out the differentiability of that function between these points, and then find out one point such that the slope is parallel to the joining fa and fv. That's our idea. So to do this, firstly we have to find out the endpoints value. So f of 2 is equal to 2 into 2 square minus 4 into 2 plus 5 is equal to how much? This is 8 minus of 8 and plus 5 is equal to 5, and f of 5 is equal to how much? 2 into 5 square minus 4 into 5 plus 5. So this is equal to 50 minus of 20 plus 5 is equal to how much? 35, right? And then f dash of x can be calculated. So this is equal to 4x minus 4, and f dash of c can be calculated. If I suppose then f dash of c can be calculated, f of b minus f of a divided by b minus f. Here f of b is equal to 35 minus f of a equal to 5 divided by b is equal to 5 minus 2. So this means we have 30 divided by 3 equal to 10. So we have calculated here f dash of c as a 10. So look at this one, f dash of c is equal to 4 into c minus 4, and it is given as equal to 10. So this is equal to 10. So 10 equal to 4c minus 4. So this will give you 4 of c equal to 10 plus of 4 equal to 14. So therefore c is equal to 14 by 4 is equal to 7 by 2. This is equal to 3.5. So as 3.5 lying between 2 and 5, see here, this is 2 and 5, so 7 by 2, 3.5 lying between 2 and 5, and its slope is nothing but it's equal to 10, which is equal to the ratio between the functional value, endpoints value, and the argument value. So f dash of 3.5 is equal to f of 5 minus f of 2 divided by 5 minus 2. That's verify Lagrange mean value theorem, right? So I think these three examples are enough to understand or to explore the statement and their proofs. The proof are quite easy. The proof was based on the previously proved Rawls theorem. So that is the one significance for that. We have to construct firstly a function phi of x such that fx plus of ax or minus of x, whatever you have to construct. And since fx is a continuous and differentiable function, x is a continuous and differentiable function, capital A is nothing but it's a constant. So the sum of the two continuous function is continuous. So phi x is continuous. Similarly, sum of the two differentiable function is differentiable. So phi x is also differentiable function, right? So that makes phi x as a continuous function as well as differentiable function in that interval. And we have chosen A such that phi a equal to phi. So it is equal to, the endpoints are equal. That makes these three conditions as the Rawls theorem. And since Rawls theorem says that for the interior point C, f dash of C is going to be 0. So phi dash of C is going to be 0. Once you are using this one, phi dash of C is equal to 0, this will give you phi dash f dash of C is equal to fb minus fa divided by b minus a. That was the tricky one to solve it, and I believe that this will enhance your concept about the Rawls theorem as well as the Lagrange mean value theorem. So thank you so much.